All right, everybody. Today we are going to talk about transformations of functions and just exactly what that looks like. So in general, in the English language, the word transform means to change, right? So that's what we're looking at doing here. We're going to take some functions and we're going to transform. And what I like to tell my students before they can do the transformations is it would help if you knew what the basic graphs looked like. So for instance, there's something they call a library of functions. And I don't care if you know that particular terminology, but inside of that library of functions, it gives you the basics and what everything looks like. So for instance, it looks like this. They call them the common graphs. If I have a constant function, that would be just my y equals a certain number like 3 or 4 or whatever, then it's a flat line straight across like that. And then I have the identity function, which the original is y equals x. It goes right through the center, right through the origin right here. And that one is basically the foundation for anything that is a linear equation. So whenever you say f of x equals x, I could also later do things to this like multiply by 2 or add 3 or things like that. Okay. And then we have the absolute function value. The absolute value function, which is where they put the little brackets around it. And we know that technically what they're saying is, that looks a little fuzzy. I'm sorry. There, maybe that's better. Maybe not. It's irritating. Okay, anyway, so they put the brackets around the X, and I tell people absolute value starts with a V, and the look of your graph is a V to begin with, because whenever you put in the number, for instance, X equals 1, the absolute value or how far that is from 0 is 1. When you put in X equals -2, how far is, or I'm sorry, -1, how far is -1 from 0? It's 1 unit. So I get a +1 as well. So for these guys on the right-hand side that are positive, it's just like over 1, up 1, over 2, up 2, over 3, up 3. So it looks the same. But on the negative side, we get the same number. Instead of when I put in a -1, I get a 1. But it changes to a positive. Okay, so it's always a positive there. And then you see down here that the quadratic functions look like a parabola and that the square root functions look like a parabola that was knocked on its side like this. And notice that they don't give the bottom half of the parabola because, as we know, if we had the bottom half of the parabola, that would not be a function, right? It wouldn't pass the vertical line test. So they only deal with the positives whenever we're dealing with a square root function. And then this lovely S curve is x to the third. That's what its basic graph looks like. And then we're going to do other stuff with it. And then if it was the third root of x, it looks like we just took this guy and flipped it over and it's on its side and rotated basically. So, and this is a function, right? Because we're only ever hitting one value with a vertical line test. So those are the basic graphs that we're going to end up doing stuff with. And so it ends up looking like, well, you know, we got this original function and we're going to do stuff with it. The one that I like to use the most is normally y equals x squared, or f of x equals x squared. And so they're telling me again up front that this is a function and the original function looks like this. It's a parabola. If you want to put points in there on your x and your y, it goes over 1, up 1, right? And the -1 squared is the +1. And so that beginning part of it kind of looks like the y equals x guy. But then when I go to 2, it goes up to 4, right? So it shoots up pretty fast, 2, 4. And then 3 goes up to 9 and so on. Okay, so that's what the original function looks like. But we're going to talk about what happens whenever I do a transformation on these. That's what we're looking at. So for instance, I'm going to grab my graphing calculator. My battery is running low on it, so hopefully it will hold out with us. If I go up here to this top line, that's my graphing row. I have y equals, and I punch in x The X is right next to my alpha button, so X. And then I need squared. You can do it a couple of different ways. There's an X squared button right here. If you go to the 7, go left 1 and up 1, it's X squared. It looks like that. Or I'll show you another way to do it. If you do X, and then you've got this little caret top here is what it's called. So go to the division on the right-hand side, go up 1. That's the raise 2 button. And then I can put in a 2. And see that it makes it look like the other. If you have a little bit older calculator, it won't look exactly like it. You might see the raise 2, the caret top there, but the end result is going to be the same because when I tell this thing to graph it, there's the first one and here comes the second one right on top of it, right? So let me change this just real quick so we can see that second one coming through. It says it's red. I'm going to change it to the little ball, the little bouncy ball, football looking thing so that we can see it better. Because here comes the first one again. The second one's in red, but now we see the ball go through, right? So they are the same graph, and then I'm going to start doing things to them. So in your whole big old world of what you're going to do to stuff, there are basically 4 things we can do. We can shift up and down, which is called a vertical shift. Vertical shift up and down, right? And in order to do that, it will look like we take whatever function we had to begin with. And on the outside, I'll either add or subtract a number, okay? So what I want you to start thinking is that the Y is the up and down, right? And things that affect the Y are going to happen outside of this function, okay? So x squared plus 3, for instance. So shifts and stretches is what we call them that affect your Y values, which is vertical, are normally outside the function. That's where they happen, okay? Outside the function. And in this case, the function, the original function is y equals x squared, right? Outside the function. So if I want to move this thing up and down, then I've got a plus 3 out there. When I come over here, I'm going to keep this original guy there, the y equals x squared. And then on the second line, I'm going to work on this. And I'm not always going to use a graphing calculator. I just think it helps to show it pretty quickly. So I said plus 3, right? So I'm going to do plus 3. And so whenever you're doing vertical, it pretty much is what you would expect it to be. It's intuitive. I look at it, I see I'm plus 3, and I'm going to add 3 to every point on this graph, right? So for instance, we have the point 0, 0. If I add 3 and I'm adding it on the outside, I'm not adding it in here, right? I'm adding it out here. So if I put in 0, 0 squared, that's a 0, plus 3, I'll get 0, 3, right? So it shifts this point that was at 0, 0, shifts up 3. Okay, and then this point was 1, 1. So let me stick in a 1. 1 squared is 1. 1 plus 3 is 4, right? So of course I didn't leave myself enough space, but there I am. Okay, and then same thing with -1. It was -1, +1. Now I'm going to do -1 squared. -1 times -1 is 1. 1 plus 3 is 4. And we know that this graph is symmetric because this is an even function, right? Symmetric around the y-axis. So everything looks the same. We know how these act overall whenever we know it's an even function. And hopefully it looks like I picked this graph up and just shifted it up 3. Okay, so let's make sure the graphing calculator agrees with me. I've got y equals x squared plus 3, and I'm going to tell it to graph. Here's my original, and there's the other one. Okay, and again, hopefully it looks like we shifted it. And if you've been doing any x-intercepts and y-intercepts, which we've had some of those definitions in this class, the y-intercept is where we cross the y-axis. The x-intercept is where we cross the x-axis. it took this intercept and it moved the intercept up, and then the rest of the graph went with it, right? So I think it's easier to graph whenever you move the intercepts first and then you deal with the rest of the graph. Okay, so we'll get some of those that we'll see, oh, this does weird stuff. Okay. But for right now, we're just dealing with this vertical shift up and down. Okay, so that was a positive. What do you think would happen if I put in a negative? Y equals x squared minus 5. Again, I haven't done anything inside my function. My function still looks like x squared, but we subtracted 5. So in my mind, whenever I'm dealing with shifting up and down, I'm looking at this and I'm going, oh, to subtract 5 means to move down 5, right? So how much is that? So we think it'll look, let me draw it right here. This 0, 0, again, I'm going to move the intercept 1, 2, 3, 4, 5. It's going down here. And then you can do points if you want to. It was 1. We subtracted 5. That's going to be negative 4. This y value was 1. We subtracted 5. It's going to be negative 4. So you can see it's still doing the over 1 up 1 thing that it did up above. Okay. It keeps the same basic shape and it just shifted the whole thing down 5. So let's see what that looks like. I'm going to put it down on this third line for us. Y equals x squared. Go over minus 5. Make sure when you do this that you use the minus 5 because it's an operation, right? I'm subtracting 5. It's not negative 5. You'll get an error if you try to use your negative. Okay, so minus 5. And again, we think it's going to take the original graph and move it down 5. So let's see. There it is. So hopefully they all look like the same graph, just it's a matter of how high or how low they are. Okay, so that's what's going on with vertical shifts. Okay, up and down. And then the next one would be a horizontal shift, right? So we want to talk about those. And we know horizontal shifts, horizontal stuff is the x values, right? This is on the x-axis, which is the horizontal line. So things that are going side to side are going to deal with my x values, okay? And for our purposes, what that means here is that we're going to take this y equals x squared, but instead of doing on the outside, I don't want to go up and down. I want to go side to side. So when I start talking about side to side, those things are going to happen inside the function. Okay, so let me scoot this a little bit so we can put that here. Shifts and stretches. That affect my my x values, or switching, are normally occurring inside the function. Okay, those things normally occur inside the function. So I'm not going to add or subtract. And we figured out that the shifts, by the way, are adding and subtracting, right? So when I add and subtract, it moves up or down. So I think that I'm going to, if I want to shift, I'm going to still use add and subtract, but now I'm going to do this inside of the function. So my function is something squared, right? That I'm dealing with, same function. And I'm going to do the same things we did up above, x, but I'm going to do it inside. So x plus 3. So those are going to be in the parentheses. And again, this is where the parentheses really pay off for me. They really make a difference whether you have them or not. So x plus 3 squared. And before I punch this in, I'm going to say, normally the horizontal shifts are against your intuition. Okay. So for instance, if you just saw a plus 3 and you were thinking left or right, you would think positives are to the right. Okay. And this is going to be opposite of my intuition. So I want you to know that going in. Things that go side to side are not necessarily the way you feel like they should go. Okay. So, and here's the reason why. I will tell you. What we're talking about here, remember I said about that x-axis or the x-intercept here? What we're talking about is we're going to move this intercept either left or right, okay, side to side. And that's the x-intercept. So if I come over here to x equals 3, then what would I have to have in order to get that as an x-intercept? So what that means is this. If I wanted this point right here from, let's just say a nice, pretty linear thing that's going on inside of the square, I would say x something equals 0 because that's an x-intercept. It's got to be a 0, right? Okay, because the y value equals 0 here. So what am I doing? If I said plus 3 and then I solved it for x, I would have to subtract 3 on both sides and I'd get x equals -3, right? Okay, so that is not what I'm doing here. So we have to be careful. I want it to be x minus 3 equals 0 because when I solve for 3 there, I'll add 3 to both sides and I get x equals +3. So if I think my intercept is going to end up over here, it has to come from something that looked like x minus 3, because when I do the opposite operation, that's what's going to make it a positive. Okay, so let's go ahead and actually physically solve this one for what that x-intercept looks like. Remember, if you want an x-intercept, you're going to plug in 0 for y. So 0 equals x plus 3 squared. Take the square root of both sides, right? Okay, that's going to go away. What's the square root of 0? In my head, I hear you saying 0. 0 equals x plus 3. So when I solve this for x, I have to subtract the 3 off both sides, right? -3, -3. That'll go away. So I have x equals -3. So if I have a plus inside of my parentheses, why did we just freeze? Give me a second. I don't know why it is doing that. Oh, there we go. Okay, if I have a plus on the inside of my parentheses here, then what it's going to end up with once I find my x-intercept, right? That's my x-intercept. What it's going to end up with is a negative. So what that means for my graph up here is that this one is going to go to -3 and 0. That's what's happening to my x-intercept. Now, I didn't do anything else to the graph, right? I didn't multiply it or stretch it or anything like that. Multiplication is going to be stretching. So this graph should look exactly the same over here as what it did at the origin. It's just that we moved the x-intercept, right? Okay, you stinker, why are you doing that? There we go. Okay, so it's just that I moved the origin, moved it from the origin. All right, I'm going to have to pause and I'll come back. I'm going to have to play with this upper cam and see what's going on. All right. Okay, I think it's working now, so we will see how it does. Okay, so anyway, as I'm doing this, I'm looking at it going, this guy moved left 3. So if intuitively you saw that +3 inside of the parentheses and you thought, oh, positive is to the right, you have to fight your instinct and you have to say, nope, we're going to go the opposite direction. And so the x-intercept will solve and go to the -3. Now, I don't have to do this all the time. If I know that it's going to be opposite, I could have just said, look at that. I mean, you can take it out and you can set it equal to 0 and find what your x is, but I can just look at that and say it's going to be the opposite. So what's going to happen to my x-intercept? It's going to move left 3, right? Left 3. I'm sorry, I didn't write earlier what they were doing. So let me go back in just a second, but it's going to be not the way you think it's going to be. So I'm sorry, this was up 3. Normally I write it out there. This means up 3, this means down 3 or down 5. Okay. So we move this graph to the left by adding inside of the parentheses. What do you think is going to happen if I need to, stinker? What do you think is I need to happen if I want it to move to the right? It's not a +3 in the middle. It's going to be, and we're going to do -5. Okay, so we can see what that looks like. So let me go, I'll bring the graph back in just a second. If it was y equals x -5 squared, we think if we're going by what we think, but what we just said, we think this is going to end up being x equals +5 for my x-intercept. Okay, because it's the opposite, which means I'm going to pick up that x-intercept and I'm going to move it what? Right 5. That's what I'm hearing in my head. Right 5, right 5. Okay, because it's all about, there's a negative in there, but it's not going left. It's going to go right. Right 5. So let me go back to my graphing calculator because I now realize I didn't do this one on the graphing calculator. And let's see what it looks like. Okay, I'm going to, here we are, come in here. And instead of having the +3 on the outside, let me delete those. And I'm going to come in here where the function itself is, and I'm going to insert. I'm going to put in my parentheses. You don't have to do all this. I just want to show us what's going on. It was +3. I'm going to put my parentheses, and then we're going to square all that, right? So that's what we were hoping to see. And let me turn this off for just a second. We're not going to graph that third one. We're just going to graph the one we think should be going left with the original. There's my original. There's my one that moved left. Okay, so we've got that good. And then while I've still got the graphing calculator out, let me go ahead and do the third one, which is we think it's going to go down, or I'm sorry, go right. This was going down, right? But I'm going to delete those. Oops. Start over, I guess. Y equals x -5 raised to the second power. Okay, so what we said was we think this one's going to go right. We're going to graph it, and there it is. It went to the right 5. Okay, so indeed, we are getting what we said we would get. So it just picked it up, and I'm out of space over here. I'm sorry. There's x equals 5. We move this intercept, boom, and then we just say, and the rest of the graph goes with it. If you want to graph a few points, then you can. So for instance, whenever I come over here, I don't know why it's doing that. I'm so sorry. So for instance, whenever you come over here, we know that the original function, when x was 1, y was 1. So you could plug in, what if x is 1 here, right? So, and then you would see, okay, 1 minus 5, that's a -4, and -4 squared, that's a +16. So on this graph, hopefully, and we can't see it, but we would have 116. What about if we put in, let's say 4, because 4 should give me like a 1 value, right? A +1, because I shifted it all over. So what is that? Y equals 4 minus 5 with the parentheses squared. That's a -1 squared. -1 times -1 is a +1. So even though I shifted this over, I still have the point 4, 1 right here. And if you put in a 6, if you want to check your values, you could put in a 6 and you could see, yep, the 6 works also. I also get a +1. Okay, so that's all fine and good for whenever I'm dealing with a nice pretty parabola that we recognize and we can just shift it around. But then the question comes up, what happens if it's a weird graph? And the answer is they all work the same. So your absolute value will shift the same ways, your square root value or square root function will shift the same ways, all of that. So I'm going to give you an unusual graph and we'll see what we think about it because I want it to be something unusual. And normally when they're unusual, it's difficult to graph them and stuff like that. So what if we were just told, hey, we've got this weird little curvy graph and we're going to call that g of x. Okay, here's my x and here's my y. And then maybe it crosses here at 0, 3, okay? And maybe this minimum down here is at 3, 2. Okay, so I'm just going to give us a couple of points that we can play with, okay? And then I said, okay, what I want you to do is graph the transformation where it does this, and I'm going to give you two at the same time. So g of x plus 2 parentheses minus 4. Okay, x plus 2 and minus 4 is what I'm after here. All right, so let's just talk about this. The one on the outside is the vertical, right? Vertical shift. And we said that that goes the same way we want it to go. We think it should go. So that means this graph is going to shift down 4. Are we okay with that? All right, down 4. And then what about the one on the inside? This one is the horizontal shift, right? But that one's going to go the opposite direction, we think. So instead of going plus 2, meaning to the right, it's going to go, the x-intercept moves to the left 2, basically, right? That's what happens here. So this is left 2. All right. And you can do shifts in either direction you want to, but later, whenever it gets a little more complicated, and we have more stuff all happening at once, we're going to want to do this kind of as the order of operations. So I'm going to do inside of the parentheses first, and then we'll do with the other. So this point right here, it's a 0, 3. It's going to go left 2. So it's going to end up right there. And this point, the 3, 2, is going to go left 2. So I'm just doing the shift to the left for right now. Oops, it should be up a little bit because this 2 right here. Okay, so I just shifting those 2 points, but I know the rest of the graph is smooth and continuous and it's sitting in there between them. So that graph, when I moved it, all I did was move it left 2. It's going to look something like that, right? Okay, so that's the shift to the left. Am I finished? In my head, I hear you saying, no, Dr. Webster, you're not finished because you still have to do the down 4, right? So we moved it to the left 2. By the way, I can keep points on this. If I moved, and this affects the x value, if I moved this left 2, that's a -2 and a 3. And if I move this one and it affects the x value, I moved it to the left, and that's, and 3 becomes a 1 and 2, right? Okay, so absolutely we can do that. And then we want to move these back and talk about this -4 thing on the outside, right? So move it down 4 is what we're saying. Well, so this, I'm just going to shift it. 1, 2, 3, 4. But when we look at that, when we shifted that value, that affects the y value, right? We're still here at x equals -2, but the y went down 4. So 3 minus 4 is -1. So my new point there that was this y-intercept up here, it moved over and then it moved down, right? So it's down here at -2 and -1. Okay. And what about this one? This one moved over 2, but now I need to go down 4. 1, 2, 3, 4. So this point was, it was originally 3, 2, and we moved it over until it was 1, 2. That affected the x value. But now this vertical shift is going to affect the y value. The x value is going to stay the same. It's still a 1, but we were at 2. So when we came down, we went 1, 0, -1, -2. So now this point is at -1, -2. But the shape of the graph is still the same. We're not changing anything as far as what my graph looks like. So this still is doing that curvy thing that goes through those 2 points, okay? When I'm doing a curve like this, I like to have at least 2 points. If it was a parabola like before, those are symmetric, so it's nice and easy to just do the x-intercept. But here I did the y-intercept. There weren't any x-intercepts on this original graph, right? So I did the y-intercept and then I picked this minimum point here and moved it around, okay? But that helps me to keep the basic shape of the curve the same. So it looks something like that. Okay, so that's how the shifting goes. And hopefully that all helps you and you're okay. You understand what's going on. It's not so bad. Okay. And then the other thing I mentioned was the stretching. And normally the stretching has to do with multiplication. I'm going to go back to parabolas. So whenever I want to do multiplication or division, because division is just the opposite of multiplication, right? Whenever I want to work with that original parabola, okay, here he is. We know this is 0, 0. If you need it, this is 1, 1 and negative 1, 1, right? So it might not look exactly symmetric, but it's supposed to be. We're going to say that's y equals x squared. There's my x, there's my y. Okay, so that's the original. And whenever I start doing stuff where I am multiplying, that's going to be what we're calling stretches. So as I look in your book, and I know you guys are all on the ebooks on the My Math Lab, but here it is, what it looks like: vertically stretching and shrinking graphs. So you can see that what they're saying is let f be a function and c is a positive graph, okay, a positive real number. Whenever I multiply by c, and again, we're going for vertical stretching, and when I multiply by c, it's going to stretch it up and down. Here they have their original graph, the blue, and then the more maroon colored graph. See how it's taller? And it's taller by a factor of however big that C is. So what they're telling you here is, okay, look here. If C is greater than 1, it's going to vertically stretch it. Okay, it's going to make it taller. Okay, vertical, up and down. It's going to stretch it. But the question is, what are they doing here in the second one? Okay, again, I have my original. It was the blue. They're doing blue for all those. But now I have this C guy multiplied in front, and this is shorter. It's not as tall, right? So all they did different was they have the C guy multiplied out in front. Again, that's vertical, but instead of stretching, it's going to shrink it, okay? So it makes it shorter, and that happens, you can see, whenever 0 is less than C is less than 1. So in other words, whenever I'm multiplying by a fraction between 0 and 1, right? That's what the 0 and 1, the things that are between there, those are fractions, right? So, or decimals, however you think about it. So whenever I do that, it actually shrinks it. So here it goes. We got vertical stretches and shrinks. Stretches and shrinks occur when I multiply, and we could say divide, but I'm just going to say multiply because we can multiply by a fraction, right? If we need to divide on the outside of the function. Again, it's vertical, which is affecting my y values. So it's going to happen on the outside of the function. And it affects how tall your y values are. Okay, that's what it does. It affects how tall your y values are. So whenever I look at that and I say, again, whatever I'm multiplying by is bigger than 1, it's going to make it taller. So for instance, what if I had y equals 2x squared? This is multiplied and it's on the outside. It's going to be a stretch and it's going to make it twice as tall, right? That's what the 2 tells me. So it's instead of being a factor of 1, which it normally is, there's normally a 1 sitting out in front, right? But I'm going to have twice as tall. So whenever I look at this and I say, hey, look, it was, by the way, this point is 0, 0. What's the y value there? It's 0, right? Okay. So if I multiply my x squared by, which was 0, okay, the y value, by 2, what's 0 times 2? Just 0. So if I have x-intercepts, they should stay anchored to the x-axis. And that's what's going to stretch this and make it tall. This guy staying anchored because even though I have 0 squared is 0, 0 times 2 is 0, that means he's not moving. Okay, even though I multiplied it by 2, it's not, that point's not moving. But what happens here whenever I put in x equals 1? 1 squared. 1 squared is 1. 1 times 2 is 2, right? So I put in a 1, but I'm getting out something that's twice as tall. It actually looks skinnier, but it's not skinnier. Skinnier would be side to side, right? That would be a horizontal. So we'll get to that one. But this one is twice as tall. It's a vertical stretch, okay? And the same thing would happen if this was a negative, right? I'm just going to stick a -1 right here. Whenever we had -1, we got out +1. Here, if I put a -1, -1 squared is 1 times 2, it's still a 2. So that's my lovely symmetry that's going on here around this x-axis. Okay, so if my, and they call it C, is greater than 1, then your graph is taller. Okay, and then they have if your C is between 0 and 1, then your graph is shorter. So let's just think about that. What do we think if we were talking about something that was y equals 1/3 x squared? Let's examine that. 1/3 is being multiplied, so this is going to be a stretch or a shrink, okay? And whenever I look out here, this is happening on the outside of the function, right? So it's going to be a vertical stretch or shrink. And then I look at it and I say, but it's 1/3, so it's going to make it shorter. So if I multiply my y values, let's use 1 again. Oops, I'm sorry, not 2. Let me try again. Y equals 1/3 times 1 squared. If I multiply my output here, 1 times 1 is 1, or 1 squared is 1, times 1/3, what do I get? A third, right? So this guy is going to be 1/3 as tall. So this one was twice as tall when I had a 2 out in the front, twice as tall. If it had been a 3 out here, it would be 3 times as tall. If it was a 5, it would be 5 times as tall. But this one is 1/3 as tall. 1/3 as tall. So we need to divide everything by 3, basically. So this point here, instead of being 1, 1, whenever I multiply by 1 by 1/3, I get 1/3, right? So it makes it wider. But we're not going to talk about side to side. We're going to talk about up and down. And up and down, it makes it shorter. Sorry, I used the wrong word there. So it is definitely shorter. 1/3 as short, right? Or 1/3 as tall. Okay. So this guy up here, he was green. He's the y equals 2x squared. He's taller. And this guy down here, he was red. Y equals 1/3 x squared. So he is shorter. Okay. And then the question comes up, what if it was negative? If C is negative, all the stuff we just talked about is still true, but negative as tall would do what? Instead of being up here, like let's just try y equals -x squared. If I stick in a 0, I keep the 0, that stays planted, but then 0 squared times -1, that's still 0. But what if I put in a 1? 1 squared is 1, but I get out a -1, right? -1 squared is 1, but then it's going to be negative because there's that negative sign out in front, right? So here's what it looks like. Y equals -x squared. So hopefully you're thinking it flips it, right? And it does. The graph flips around the x-axis. Okay, and that's exactly what's happening here if we see it doing that. Okay. All right, so those are the verticals. And again, I can do some of this on my graphing calculator so we can see what's happening. Let's use a different graph just than the x squared, just so we can see it works on all of them. Let's use x cubed. Oops. Well, there we go. X cubed. And if you know your basic functions, that guy is going to be, clear that. The x cubed guy is going to be like a curly or an S curve. It goes through the origin. And then we're going to go, let's make it really dramatic. Let's make it 4x cubed. Okay, and then I'm going to clear that one out down there. And let's graph it and see. Here's my original. It looks like an S curve. And then look at that. It is taller, right? It's 4 times taller. Instead of 1 and 1, I have 1 and 4. It's way up there. Okay, so definitely it is stretching it vertically. And then let's try y equals negative x cubed. What do we think that's going to do to us? Hopefully we're saying it's going to flip it around the x-axis. So things that are on the top are going to go to the bottom. There we go. And things on bottom went to the top, right? So it just flipped it around the x-axis. And then what if it was, let's do 0.5 x cubed. Okay, 0.5 is really the same as a half, right? So I got rid of the flip because I don't want to see it in there. So this should be half as tall, right? So there's the original, there's the tall guy, and here's the, there he is, half as tall guy. Okay, so he looks a little flatter through the middle is what happened there, okay? All right, I did not set a timer, so I'm wondering how long this video has been going. Let me check real fast, see if I can do anything to find out. I think that's about all my time. So what I'm going to do is I'm going to stop there, and then we will pick up horizontal stretches and shrinks, and hopefully we can cover that in class and answer any questions you have over all of this stuff. All right. Okay, I'll talk to you soon. Thanks and have a great day.